Okay, last hour of Physics 1C for November 29th. In this last hour, we're going to talk about power in AC circuits, and we're going to talk about transformers. Okay. Okay, so in the past, what we've learned is that power in an electrical circuit is just current times voltage. And that is going to be no different in this case. In this case, what we're going to be able to define is the power as a function of time should be equal to, the current in our case, we've been saying was equal to I max times the cosine of omega t, while the current, the voltage, I should say, is given by V max times cosine of omega t, and now we have this phase angle that's showing up now. So what we would like to do is to average the power over one phase, similar to what we did at the beginning of class today. So what we'll do is we'll say, let's find the average power. Well, let's multiply this out, first of all. So the first thing we can do here is we can use the same identity we've been using all class. Here, we'll put I max, V max in front. And we'll put the cosine stuff together. So it's cosine of omega t times cos omega t plus phi is the same thing as cosine of omega t times the cosine of phi. This is plus, so we make this minus the sine of omega t times the sine of phi. Okay. And now what we're going to do is we're going to time average this function over one period. So we're going to say the average power should be equal to, so we do this exactly the same way we did before, which is that we're going to average these functions here, right? But when we look at these functions, what you might notice is that there's two of them. There's this one, which has a cosine squared in it, and there's the other one that has a cosine of omega t sine of omega t times the sine of phi. And what we need to do is we need to find the average value of these functions, which basically means that we have to time average them, so we have to integrate over one period and then divide by the period again. If we do that, because you have a cosine and a sine right here, if I take this function, so this is basically the idea. If I take cosine of x times the sine of x, right, dx, and I integrate over one period, then what's going to happen is that this function is going to be equal to 0 if we go over one period from 0 to t. This is going to be 0. That's because it's a cosine and it's a sine, and it's, yeah. But if I take this one, and you'd have to divide by t too. In fact, I shouldn't be doing this with x's, I guess. I think that's probably too confusing. Maybe I'm confusing you. Let me not confuse you. So if it's cosine omega t and sine omega t dt, that this will be 0. But if I do from 0 to t of cosine squared of omega t, which is what the other function... See, there's a cosine squared here, and the other one is this one. And phi is just a number. If I do this one, though, I believe we figured out that this was equal to a half, right? So what we get out of this whole thing is that the average power, we did this at the beginning of class, so you can go back and look at it. The average power now is going to be I max V max times a half, so divided by 2, and then multiplied by cosine phi. But this 2 is the same thing as, the square root of 2 multiplied by the square root of 2, and I max over root 2 is I RMS, and V max over root 2 is V RMS, and then we have this cosine phi thing hanging out here. So this is why cosine phi is referred to as the power factor. We call this the power factor. Because unlike with DC circuits, where a DC circuit you just have I times V, with AC circuits, you get I times V times this thing. And if you think about what phi was, we go back. What was phi? Phi was the angle between the current phasor and this phasor, the kind of total phasor. So this phi here, when it's not equal to 0, will actually reduce the power coming out of your circuit. And what that implies is that the maximum power that you can get out is when cosine phi is equal to its maximum value, which is 1. And that's only going to happen if phi is equal to what? What does phi need to be for cosine phi to be equal to 1? What does phi have to be? Zero or pi or 2 pi or something like that, right? But we usually think of phi as being an angle that's always, I think it's always acute. So it's either, phi is always between negative 90 and positive 90, or negative pi over 2 and positive pi over 2. So yeah, so if phi equal to 0, then you get a power factor of 1, which is the biggest that you can possibly get. And that implies that your system is as efficient as it can possibly be at taking the input power and converting it to output power. Okay. Now, we can write this in a slightly different way, because we also know that cosine phi, as we saw above, was equal to the ratio of the resistance of the circuit divided by the impedance of the circuit. And if we plug that in here, and then do VRMS over Z, we know that this is IRMS, so we get this relationship. And that's pretty neat, because this is exactly like what we have for DC circuits, except it's RMS current. So I squared R is still what the average power output in one of these circuits are. So why is that the case? How come the inductor and the capacitor don't show up here? Why don't the inductor or the capacitor show up in this equation for power? Does your book even write this equation down? Oh, they say they leave it as a proof for you. Yeah. Anyway, why do the inductor and the capacitor not show up in this? In this final equation here? What do you all think? You can answer in a way that you can prove mathematically why they don't show up. Maybe you could come up with a conceptual reason why they don't show up here. Why is it just the resistor that's showing up here? That doesn't really answer the question at all. Sorry, I don't mean to be rude, but what do you all think? Why does the inductor and the capacitor not show up here? V equal to I times Z. I'm going to write the question down because I don't think the... Is energy only lost in a resistor? That appears to be what it's saying, right? That's basically the right answer, Josh. The energy is really only dissipated through the resistor. The inductor basically can store energy inside of its magnetic field. But the thing is that with an inductor, it can either be charging up or discharging. Same thing with the capacitor. The capacitor can either be charging up or discharging. When the capacitor is charging up, there's power going into it, right? When the capacitor discharges, the capacitor acts as a source and delivers power back to the circuit. No, that's not the right answer. No, that's not right. They don't cancel each other out unless XL and XC are equal to each other. That's the only time that they're going to cancel out. In this case, they're not. That's not the reason why. The main reason is because both the inductor and the capacitor can act either as a sink for energy and a source for energy. When they're being charged, there's energy going into them. When they're discharging, there's energy going out of them. And that's the reason why, basically. So, the resistor, it's always giving off energy, right? Think about what a resistor does, right? So you've got a resistor, right? A resistor doesn't care if the current goes this way or if the current goes this way, right? These molecules in here are still going to vibrate, and that's still going to send heat out into the environment, right? It doesn't matter if the current goes this way or it goes that way. What the resistor does is it converts electrical energy into thermal energy that's given off as heat, right? And that happens on both sides, on kind of like both strokes, effectively, going this way and this way. So that's why. Only the resistor is always going to dissipate energy. The other two pieces won't. Now, the reality is that we're still treating the inductor in this case as if it's a pure inductor, and that's kind of impossible. The reality is that the resistance represented here would have to represent the resistance of the entire circuit if this is going to be real. Okay, so we've got this definition. One thing I'm going to say here is that I'm just going to read to you the way that the book says it, because I think that the way they say this is really good. In fact, do I have the book open? Let me just pull the book up so I can show you what they say about the power factor, because I like the way that they state it. And I kind of said something, but they just do a better job. So what the book says about the power factor, if we go to here, is here. Okay. A low power factor, a large angle of phi, is usually undesirable in power circuits. The reason is that for a given potential difference, a large current is needed to supply a given amount of power. This results in large I2R losses in the transmission lines. Many types of AC machinery draw a lagging current, that is, the current drawn by this machine lags the applied voltage, hence the voltage leads the current. If the voltage leads the current, that means phi is greater than 0 and cosine phi is less than 1. The power factor can be corrected. We're going to do this in one of these problems here. They don't do this in your book, but you'll see it show up in your lab manual homework, and I'll show you how to do it. The power factor can be corrected to the ideal value of 1 by connecting a capacitor in parallel with the load. The current drawn by the capacitor leads the voltage, that is, the voltage across the capacitor lags the current, which compensates for the lagging current in the other branch of the circuit. The capacitor itself absorbs no net power from the line. So the idea is basically that if you want to get a cosine phi that's equal to 1, what you could do is you can add things to your circuit. And that may make your circuit more efficient because, as they say right here, the reason is that for given potential difference, a large current is needed to supply a given amount of power. So if you want to lower the amount of current that you need to supply the same amount of power, you might be able to fix the power factor. That's basically what they're saying here. I don't know if that made any sense, but anyway, point is that we can manipulate our circuits to make this closer to 1 if we want to. And maybe there's systems in which you don't want to do that. All right, so let's look at these problems. Maybe I could give you an example. No, we'll do that when we talk about... I was gonna give you an example, but we'll do that in a second as to what the power factor really is and what it means for it to be equal to 1. Okay, power in a hairdryer. Okay, this is a really easy problem. An electric hairdryer is rated at 1500 watts. That's our average power, so we can write that down. Power average is 1500 watts. At 120 volts, that's the RMS voltage. They're so nice to tell us. VRMS is 120. Part A says to calculate the resistance. Part B says to calculate the RMS current. C, the maximum instantaneous power. Assume that the dryer is a pure resistor. Okay. Well, this problem's pretty easy. So if it's a pure resistor, that means that R is equal to Z. And to see why that's the case, Z is the square root of R squared plus XL minus XC whole squared. So if it's a pure resistor, that means that this is 0, so that means Z is equal to R. If Z is equal to R, that means cosine phi is equal to 1. And we can use power average equal to IRMS, VRMS, times the cosine of phi. But if this is 1, then we're just going to take power average, divide by VRMS, and that should give us IRMS. So we're technically solving part B first, but I think it makes sense to do this. So power average was 1500 watts. Divide that by VRMS, which is 120 volts. So this is going to be 150 over 12. I don't know what that is. Let's see. I got 12.5 amps. Okay, so that's part B. We can use this to find part A, which is the resistance. So if I take I squared RMS and multiply by R, that's equal to average power. So we can find the resistance by taking the average power and dividing by I squared. So average power was 1500 watts. We're dividing by I squared RMS, so 12.5 amps, and we need to square it. This should give us our resistance. And we get 9.6. That's A. Part C says the maximum instantaneous power. I think we just multiply by square root 2. Right? Because if average power is I max over 2 times V max over 2 times cosine phi, over root 2, then I would think that the max power, it's pretty simple. The max power is just going to be 2 times the average power, because I think it's just going to be I max times V max, which should be equal to 2 times IRMS VRMS, because IRMS times Imax times root 2 is equal to this, Vmax times root 2 is equal to this, so the max power should be, I think, 3000 watts. So I did something wrong. Does that seem right to y'all? Does that seem reasonable? Yeah, that's what they say is the right answer. All right. Any questions? Pretty easy problem. Okay. Finally, we have this problem here. For the LRC circuit in 31.4, we want to calculate the power factor, calculate the average power delivered to the entire circuit and to each circuit element. Good boy. So, in that problem, I think what we found was the inductance was 600 ohms, the resistance was 300 ohms, and the capacitance was 200 ohms. We also had an angular frequency. I don't think we're going to need that. We found Z was equal to 500 ohms. We had IRMS. Was it IRMS or IMAX that was 0.1 amps? I think it was IMAX, actually. Let's see. Here we go. Yeah, it was IMAX is 0.1, and Vmax was 50. Volts. I hope that's enough information to solve this one. So part A says to calculate the power factor. The power factor PF is equal to cosine phi is equal to R over Z is equal to 300 divided by 500. So it's equal to 3/5, which is 0.6. Okay. Part B, calculate the average power delivered to the entire circuit as well as to each circuit element. Okay. Power average is IRMS times R. You have to square this. And IRMS is equal to Imax times square root of 2. So if I throw in here a square root of 2 times Imax, that's what IRMS is equal to. So we just need to square all of this and then multiply by R. So this is going to be the square root of 2 times Imax, which is 0.1, squared times R, which is 300. So this is going to be 2 times 0.01. 0.01 times 300 is going to be 3. 3 times 2 is 6 watts. Do you all agree? That's not right. What am I doing? I'm silly. IRMS is Imax divided by root 2. Sorry about that. Yeah, because IRMS is smaller, right? This is over root 2. This should have been divided by root 2, which means that we multiply by 2, but we need to divide by 2, so we need to divide by 4. So this is then going to be 1.5. Right, let's see, 0.1 squared is 0.01 times 300 is 3. 3 divided by 2 is 1.5, yeah. Okay, does that make sense? You have any questions? This is all pretty easy, right? You know I made a mistake. Okay, so let's look at how this problem can be made a little bit harder. So part C. Let's see. So our power factor is positive, right? Because the power factor is positive, we know in this case, can you all tell me? Let's see if you can figure this out. Is XL greater than XC or is XC greater than XL in this problem? So phi is positive, right? Which is bigger, XL or XC, if phi is positive? If you can't remember, I'll put the equation here. Which is bigger, XL or XC? If phi is positive. This means phi is positive, right? Actually, wait a minute. How can you guys not, I mean, L is here, C is here, come on. Oh, that's not L and C, actually, is it? These are actually XL and XC now that I think about it. That's my bad. This is XL, and this is XC. Okay, well, XL is bigger than XC. I must be going too fast, or people just aren't here or something, because I don't think that question was that hard. So I apologize. I must just be kind of losing people. We know that XL is greater than XC. It's given. But what we'd like to do is ask this question. How can a capacitor be added so that cos phi becomes 1? Okay, so we've got this circuit. Resistor, inductor, capacitor. And right now, cosine phi is equal to 0.6, right? How can we add a capacitor to make it so that cosine phi becomes 1? What would we need to do so that cosine phi would become 1, which would mean that phi would be equal to 0? Can we add a capacitor in series? Can we add a capacitor in parallel? And what should the value of that new capacitance be so that we get a power factor of 1? This is like one of your lab manual problems. And maybe even one of the mastering physics problems is like this too. Do we want to add a capacitor in series? Do we want to add a capacitor in parallel? What do we want to do? Does our capacitance need to get bigger? Does it need to get smaller? What do y'all think? We want C to be smaller. How do you know that? How did you figure that out, Josh? I'm not saying it's right or wrong. I'm just asking. You came to that conclusion. What was your line of thinking there that led you to that?
Do you mind if I answer on voice?
Please do.
Okay, because I'm looking at tangent of phi is XL
Yep.
minus XE over R.
Yep.
And if we already know XL and R isn't changing, then if we want the top part to, if we want that difference to be
What? What does it need to be?
I don't know what the difference would be, but we'd want it to be smaller.
Sure you do. You want it to get smaller. Agreed. But if phi is equal to 0, what is tangent of 0 equal to?
Uh, 0.
It's 0, right?
Yeah.
So if we put 0 in here, we know we want this to be equal. If phi is 0, then tan phi is 0, right? So if this is 0, then now we need this. The only way that this can be equal to 0, R can't be 0, right? R would need to be infinity to work out to this. So basically, the numerator has to be equal to 0, right?
Yeah.
And as you said, if we make the total capacitance of our system bigger, then it'll make XC bigger, and hopefully make it equal to this, and then this will be equal to 0, right? That's exactly right. You got it right. Okay, so series, because by adding something in series to our picture here, let's expand our circuit. If I add another capacitor here, and let's say that we call it C prime or something like that, now the equivalent capacitance of these two, CEQ, is going to be, they're in series, so we do 1 over C plus 1 over C prime to the negative 1. And we'll always get a new value that's less than both of them when we do this. Okay, so that's what we need to do. And what we know is we want this to be equal to 0, which means that XL has to be equal to 1 over omega c. And we know the value of XL, so we can find the value of C, right? So CEQ has to be equal to, what is it, XL times omega? No. 1 over omega XL, right? So this is 1 divided by, omega was 10,000, right? And X sub L, I think, was 600. Just scroll back up. It was, right? Yeah, 600. So this gives us an equivalent capacitance that's equal to hopefully you're all following along. If you have any questions about what I'm doing here, please ask. I get 1.67 times 10 to the negative 7. That's farads, right? I could then plug that into this equation and solve for C prime now. So this equation says 1 over CEQ minus 1 over C is equal to 1 over C prime. If we just put both sides to the negative 1 power, we'll get 1 over CEQ minus 1 over our original capacitance C to the negative 1 power should be equal to C prime. So that's going to be 1 over 1.67 times 10 to the minus 7 farads minus 1 over, I think it was 0.5 times 10 to the minus 6 farads, right? So this is equal to, we'll get a positive number out of this, which is good, this to the negative 1. I think I did this right. 1 divided by this minus 1 divided by 0.5 e minus 6 is that to the negative 1. 2.5 times 10 to the minus 7. 2.5 times 10 to the minus 7. So look at this. This is farads, right? This would actually be, so this is C prime. So this would actually be 0.25 microfarads, I believe, right? And that's the answer. If we add in series in our circuit, right? In series, if we add this value here, now our equivalent capacitance is now going to be equal to that, which is going to make it so that XL is equal to XC. Put XCEQ here or something like that. Whoops. And if XL is equal to XC, we get tan phi equal to 0, which means phi is equal to 0, which means you have a power factor of 1. So just by doing this, you make your system more efficient at converting input power into output power. And the reason why this is the case is pretty similar to what happens when you push a child on a swing. But before I get into that, let me just see if you all understand. Is everyone on board with what we just did? This is kind of like the hardest these problems get. Other than this, these problems are pretty easy. So if you were confused by what I just did, please ask a question. Okay. Now, there is a possibility that there's other ways to actually solve this. So in this case, what we did was I said, how could a capacitor be added? But the reality is that you can actually also get a power factor of 1 if we had just made this smaller. And I think the way you make inductors smaller is by adding inductors in parallel. But this works just fine. Okay, so something I want you to think about as a way to understand what's going on here is pushing a child on a swing, because I hope that a lot of you have an experience with this. So say you've got a swing, right? And sitting on your swing is a kid. So there's the kid sitting on the swing. And what you're going to be doing is you're going to be pushing the kid to make him swing back and forth, right? So you're going to do so by exerting a force in this direction here. So you exert a force. What happens? You push the kid. Well, now the kid is going to start to swing, right? And the kid's going to swing back and forth, kind of like a pendulum, right? Now, how do you apply this force? Well, if when you apply that force, the kid is swinging towards you, what will that force do to the kid? right? So let's say that the kid is moving in this direction when you apply this force here. What's going to happen to the motion of the child and the amplitude with which the child swings? The kid's coming towards you, and you push in the opposite direction. What's going to happen to, let's say, the amplitude with which he's swinging? It's going to get smaller, yeah. Because if the kid's coming towards you and you push on him in the same direction, it's probably going to make the kid get knocked off of his seat in reality. Because the kid's going to come down pretty fast, and if you shove this way, he's probably going to get knocked off, or, it'll get smaller. So we know that's not really a good way to push a kid on a swing, right? A good way to push a kid on a swing is to make him go higher and higher, because that's fun, right? And children want to have fun, just like everybody wants to have fun. So if we apply the force only, right, when the kid is going in the same direction, then the amplitude of the child's swing should, at the very worst, stay at the same height, and will probably grow, right? So if we push once per period, I would say, once per oscillation, in the same direction, as the velocity of the child, then the kind of like height that the child swings to will get bigger and bigger and bigger. The amplitude of motion, or the swings, will get larger. So implied within this concept is the idea that it's not just how hard we push that makes the kid go higher, right? It also matters when we push, right? We can only push one time every cycle. If we want to, we could push twice per cycle, but we'd have to change the direction, right? So if we push the kid when he's going this way, we push to the right. And when he comes and swings back down, if we then push him back the other way, we'd basically be going this, and then like this, and then like this, and making sure that each time that we apply the force that the kid's already moving in that direction, then the swing should get bigger and bigger, and the kid should be able to kind of keep swinging, right? Of course, you don't even need someone to push you to make this happen, right? You can basically, as many, I'm sure almost everybody in here has probably been on a swing before, knows that if you just kind of pull on the ropes as you come down, you can actually force yourself to get higher and higher. But again, when you do that, you need to make sure that you're always pulling on the ropes or the chains at the right frequency, right? So this implies that if you have an external force and you want to increase this quantity V, you need to be careful about how you do it. You need to be careful about the frequency with which you push, right? So in an AC circuit, the equivalent of these things are the force that's applied here is like the source voltage, okay? And the velocity here is like the current that comes out, right? And when the power factor is equal to 1, that's like doing this to the circuit. It's like saying, in our circuit, let me draw a picture of the circuit here. So we've got our circuit, right? It's our LRC circuit. So we get the capacitor, we get our resistor, we get our inductor in here, right? Depending on the size of the inductor, the size of the capacitor, the resistor size doesn't matter. But depending on these two, you're going to get the power factor thing that's going to show up. And imagine that your source is pushing in this direction while the current is also flowing in that direction. That's to say, like, electrons in the wire are going this way at the same time that the source is pushing on them, and then when the electrons go backwards, the source just pushes them back this way, and then now when the electrons want to turn around again, the source pushes them back this way. Can you see how that's almost identical to what's happening with a child on a swing? If you want things to be in phase, that will only happen if your inductive reactance and your inductive capacitance are the same, which is where phi is equal to 0. And to say phi is equal to 0 is like saying that you're always pushing in the same direction that the object wants to go. That's what it means when we say cosine phi is equal to 1 or that phi is equal to 0. It means the whole circuit is in phase with itself, right? You push the charges and they go. You pull the charges and they come back. And we kind of call this type of thing resonance. This type of thing that's going on here is what we call resonance. Resonance is the idea that you drive a system at the frequency it already wants to oscillate at. So driving a system at the same frequency that it wants to oscillate leads to max power. And we call this frequency that it wants to oscillate at the natural frequency. And we can figure out exactly what this quantity is by thinking about the LC circuits that we looked at in the past. The LC circuits had a frequency of the square root of 1 over L times C, and these RLC circuits have the exact same natural frequency. Sometimes this is referred to as omega naught. This is the natural frequency of the system. So if you look at what happens, if you do this in one of these circuits, right? If we look at what happens, for example, to XL and XC, so if omega is equal to this quantity, right? Let's look at what happens to XL minus XC, right? So XL is XL is the one that is omega times L minus 1 over omega times C. If I plug in this for my value, is this going to work out? I don't know. We'll see. It should work out. If I plug in omega naught here and here, then what we get here is L over square root LC minus, times L. Yeah, that's right. Minus, so it's 1 over omega naught. So this one's going to be square root LC divided by C. I think this is automatically equal to 0, right? Because this is going to be L over root L is like the square root of L over C. And minus the square root of C under the square root of this will be the square root of also L over C. So you end up getting 0. And this means that cosine phi is equal to 1. It means that XL is equal to XC, etc. So if you use this as your frequency, the natural frequency, then you'll automatically get these things to happen here. Okay. If we had time, we'd do one more lab where you kind of show these kind of effects. But if you look at the, I'm just going to stop with that right there. I think that's a good place to stop. We're stopping a little early today, but I think that's okay. Resonance is a really important quality for not just AC circuits, but it shows up in other places as well. Next time what we'll do is we will... oh wait, there's another problem we could do, and we have 10 minutes left. We might as well. I put it on here. But I would say next time what we're going to do is we're going to talk about transformers, and then we'll talk about electromagnetic waves. But we do have this problem that we can do. So let's do it real quick before we go. Tuning a radio. The series circuit is similar to some radio tuning circuits. It's connected to a variable frequency AC source with an RMS terminal voltage of 1 volt. Find the resonant frequency, and then at the resonance frequency, find inductive reactance, capacitive reactance, impedance, RMS current, and then we'll find the RMS voltage across each circuit element. Okay. All right, what's the first thing they want us to do? Find the resonant frequency. Okay, so we have L is equal to 0.4 millihenries. C is equal to 100 picofarads, which is 100 times 10 to the minus 12 farads. The first thing they want us to do is to calculate the resonant frequency. Resonant frequency is the 1 over the square root of L times C. So that's 1 over the square root. 0.4 millihenries would be 0.4 times 10 to the minus 3 Henry times capacitance, which is 100 times 10 to the minus 12 farads. This will give us our natural frequency, omega naught. So I got 5 million. We'll just write this as 5 megahertz. Oh, wait. Nope. forgot. It's 5 times 10 to the 6th. It's radians per second. It's not in hertz. My bad. So we get that. Part B says to find the inductive reactance, XL. So once we have this quantity, we can say that X sub L is just equal to omega naught times L. So that's going to be 5 times 10 to the 6th radians per second multiplied by L, which was 0.4 millihenries. So 0.4 times 10 to the minus 3 henries. Henries are basically ohm seconds. XL then is equal to that number times this. So I get 2,000 henries. No, not henries. Now it's at ohms. You can check for yourself. The next part asks us to find X sub C. I promise you that it will be exactly the same. Calculate it yourself by doing 1 over omega times this. In fact, I'm just going to check real quick to make sure it actually works. Divided by 100 e minus 12. Yep, I got 2,000 again. Part C. Oh, also the impedance. So it's interesting. In this case, the impedance. Are we given the resistance? Oh, it's right here. Resistance is 500. So since Z is equal to R squared plus XL minus XC whole squared, if XL and XC are equal to each other, that means that Z is just equal to R. So Z is just equal to 500 ohms. Part C, to find the RMS current, all we have to do is to say that RMS current is equal to V over Z. It says RMS terminal voltage of 1 volts. So this is RMS. So if we do 1 volts and divide by 500 ohms, 1/5 is 0.2, and then divide by 100 again, so you're going to get 0.2 times, I don't know what this is going to be. What is this? This is 0.002 amps. And the RMS voltage across each circuit element. For this, VR is just IRMS times R, VL is IRMS times XL, and VC is just IRMS times XC. And I'll leave that for you all to do yourself because it's quite easy. And I think we should stop now. So I will see you all next time we have a lab, and hope you all have a good day.